This brings us to the notion of a strong and weak acid and base. So what is a strong acid or base? It's about dissociation in water. A strong acid or a strong base will completely dissociate into the water. Example, HCl, very popular acid. Geologists are using, you always bring a little bottle of 3 or 4% HCl in your bag to test for carbonate or limestone if you are a field geologist. So this plus water will give you the famous Cl minus plus H3O plus. And how do I represent the dissociation of this acid here, this gas, into this liquid? Just by using this famous equilibrium constant, the K value. In this case, the K for an acid, we call that Ka, K for the acid. So the Ka would be equal to that, now you know, the concentration of Cl minus time the activity, if you want to be absolutely right, it's activity, but we're going to deal with concentration here because in this case the activity will be equal to the concentration because it's highly diluted. A solution, again, remember, activity is nothing else than the concentration times the activity coefficient. And if you have a highly diluted solution, the activity coefficient is 1. And if you are more concentrated, this coefficient will decrease. So the activity will be a little bit less than the concentration. But now let's do that divided by the reactant, which is HCl and H2O. This is liquid. So if you want to simplify, this is 1. It's going to be equal to the chlorine and the hydronium divided by the HCl concentration in solution. So if it's a strong acid, that means it will completely dissociate under the form of hydronium and chlorine. That means that the Ka has to be very high because this number here has to be high compared to that. I mean, this number here has to be high compared to that. That means the entire process will be transformed into a product. Ka has to be way larger than 1. Actually, for HCl, it's difficult to, there's some attempt to calculate it. The number is, for example, 10 to the power of 6. The Ka, the constant of equilibrium or dissociation constant of gas, all these K value, you will see, will have different names, but it's always the same principle. It is the product divided by the reactant. You call that the equilibrium constant. You can also call that the dissociation of gas into a liquid. Because, of course, this will turn into HCl aqueous. If you're putting a gas like oxygen into water, it will stay as oxygen and you will be having a certain amount of oxygen into your water. The same way as HCl as a gas can be dissolved into water. You can put a lot of HCl into water. So a strong acid has a very high value of K. In a similar way, NaOH, which is a strong base, plus water will give you Na plus OH minus. It will give you a Kb. We're using B for base in this case, but you understand this is the same formula. This is equilibrium constant. One is used for an acid, 1 is used for the base. When it's for a base, you're calling that Kb. When you're using for an acid, it's going to be Ka. And this is going to be equal to the concentration Na plus OH minus, and you have the NaOH concentration. The water will be the same. So in this case, I can put that also H2O in this case here because I'm putting there, here, and here. So the dissociation of this base is also very, very larger than 1. Same as a strong acid, meaning the entire processus is product and nothing is left from the reactant. So that's the definition of the strong acid. For a weak acid, the acid will not fully dissociate with the water. An example of weak acid is the carbonic acid. Will give you CO3 minus plus H plus. You can write it the correct. The hydrogen ion in this case. So in this case, the Ka will be equal to 10 to the power of minus 6.5 for 25 degrees C and 1 atmosphere. That you will see that this is quite important when we're dealing with carbonate. So this number here is smaller, way smaller than 1. That means that if you take the Kb equal the concentration of HCO3 minus time the hydronium concentration divided by the carbonic acid. Again, this is what we call carbonic acid. You will have still a large amount of carbonic acid into your solution at equilibrium. The value here is very small. That means this acid here will not fully dissociate into your liquid. And the same for the base. So in summary, a strong acid will fully dissociate, will leave all the H plus into the solution. The weak acid will let a certain amount of H plus in solution, but keep part of the reactant still into solution and not transform everything into product. Actually, the right way to write a reaction with the weak acid is to have the two sides of the arrow here. A strong acid will always go in one direction because all the reactant will move into a product. The same for the strong base, one way. For the weak acid or weak base, you will have both because it's a dynamic equilibrium. It will shift from one species to another because you will have both the acid and the base in solution. If you take an example for a base, a weak base is in the example we just saw before, plus H2O will give you the dynamic equilibrium of ammonium ion plus the hydroxide ion, which again is a dynamic equilibrium. It will, as a function of the condition, shift one side or another. And the K value, the Kb value, here will be way smaller than 1 because the reactant will not be all transformed into a product. So now we need to have a way of representing the acidity of the basicity of a solution. And to do that, we need to introduce the pH. I'm sure you're familiar with the pH, but I will reintroduce it a little bit to refresh a little bit of your knowledge for the pH. So where this pH coming from is coming from what we call the very important notion of the dissociation of the water. So it's going to be a chapter called about water and pH. So there is a very important notion called that dissociation of water or auto-ionization of water. What is that? It's very simple. When you have two molecules of water, the Lewis structure here, they're really happy together. They're making bridge, in this case, van der Waals force between the H and the O to add this liquid structure, this famous hydrogen bond that we defined in the previous chapter. But sometimes those molecules can come very close to each other. Now we're familiar with that, right? There is the positive part of it and the negative part of it. Let's be consistent here. With the negative part of it here and the positive part of it here. So this part will be attracted to this one and vice versa. But sometimes there's not only attraction. One molecule will be close enough, the oxygen will be close enough from a nitrogen to grab this hydrogen out of the other water molecules and auto-ionize the water. And this will give you one molecule of hydronium and one molecule of hydroxide. So in this case it can be H3O plus and OH minus. This is called hydronium again, and this is called hydroxide. The equation is 2H2O will give you H3O plus plus OH minus. And the constant of dissociation of this, we call that water, or Kw, equal H3O plus time the concentration of hydroxide divided by your concentration of water equal at 10 to the power of minus 14 at 25 degrees C, 1 atmosphere. Very important. What is the equation telling us? It's telling us that just in normal condition at room temperature, if you have a bucket of water, 99.9%, even more than, will be under the form of H2O. But a certain amount of those molecules will interact with each other and produce an hydronium and an hydroxide. And at this temperature and pressure, the amount of those molecules will be equal, this equation, this constant of equilibrium will be equal to 10 to the power of minus 14, which is more or less represent 6 times to the power of 16 molecule per liter. Knowing that in 1 liter of water comprise 56 mole of H2O. We're talking about 6 to the power of 16 molecule, not mole, molecule. Sorry, I should have written that a little bit more clearly. Molecule per liter. This is mole of H2O for 1 liter. So this number is very, 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 very small. But it still is here, very important. So if you're working on that, you can work with this number, which is a number with an exponential. 10 to the power of something. In chemistry, when you have those huge number or very small number, people are working with the log of it. You know that the log of 10 to the power of 16 will be equal to 16. So it's easier to work with a round number like 16 than 10 to the power of 16. What we use generally when you're dealing with k value, we're dealing with pk value. And the pk is just, by definition, minus log 10 of the value. So if I'm looking at the pkw is equal to 14. The minus log of the concentration of OH minus and H3O plus in solution is equal to 14. And we can go one step further. pKa, so let's simplify by the K of the water, equal H3O plus, concentration of OH minus, divided by the concentration of H2O. This is a liquid, so this is 1. So it's equal to the concentration of H3O plus times the OH minus, and equal to 10 to the power of minus 14. And if I'm taking the log of that, what we have is, or minus log of it, okay? Because now we want to have the pKw, which is the minus log of this value here. It's equal to the minus log of the concentration of H3O plus times the OH minus. And you know that by the log rules, this is equal to, this is a multiplication, log of A times B equal log of A plus log of B minus log of H3O plus minus log of the OH. This is, we're going to actually have, this is what we call the pH, and this is what we call the pOH, and this is a pKw. So the definition of a pH is the minus log of the concentration or activity of the H plus in solution. H plus in solution is never under the H plus in solution, is always the hydronium ion, but you will see that from now on we will simplify. We will not always write H3O plus, but H plus. So the definition of the pH equal the minus log of the activity of H plus, which in our case equal to the activity of the hydronium. But we will simplify this writing by not writing H3O plus every time. We will remove the water. So this is the definition of the pH, and this is the definition of the pOH. Again, activity and concentration, I will mix that easily here. The definition of the pH is the activity. I know we didn't discuss in detail the difference between activity and concentration. Either way, to see the difference between those two notions, the concentration is the amount of substance you have in your solution. You're putting a certain amount of a substance A into your water, you can analyze that, and this is your concentration. The activity is the part of this concentration, of this amount, that is available to do a process, to have a reaction. So you understand that if you have a highly diluted system, all the concentration, all the molecules in your water are likely to be able to be involved in a process. So the activity will be the same as the concentration. But if you have if you're evaporating your water, for example, or if you're increasing the concentration, and you start to have interaction between the elements you put in your water. You have so much elements that they start to interact with each other. Some will be will be caught in some kind of trap and will not be able to be used for any processes. So the concentration, if you analyze, you will have the same, but amount of molecules that could be involved in a process will decrease. So the activity of a substance A, for example, equal the concentration time the activity coefficient. So again, the A equal the activity, the C equal concentration, and the Y is the coefficient of activity. When you have a highly diluted water body and the elements are well dispersed, the Y coefficient of activity equal 1. That means activity will be equal to concentration. But if you start to jam pack your elements and they have, see, a little bit like a box of Lego, you know, those Lego boxes, Lego, and you start to want to build something. If you have your pieces of Lego well spread around in a box, you can choose, pick, and do whatever you want, your car, your wall, your house. But if you jam pack those Lego into something that is very well organized and very difficult to reach, you will not be able to reach the Lego at the bottom of your box. That means you will still have the same amount of Lego, but they will not be available for you building your wall or your car. So I mean, the concentration will be the same, the activity will be different. So this is a short, intuitive way of seeing the difference between concentration and activity. So for now on, we will mix both. We will look at ecosystem or example where the substances are highly diluted. So in this case, the activity will be equal to the concentration. But keep in mind that the real correct definition of the pH is minus log 10 of the activity of the H+. H+ is again a simplification of H3O+. So how can we use that now? We know that the pKa of the water equal 14 equal the pOH plus the pH. That means that the pH of a neutral body of water, again a neutral body of water at 25 degrees C and 1 atmosphere, very important, is equal to 7. And this is the origin, the source of your neutral pH at 7. So if you have a scale, 7 will be your neutral pH because any body of water, you're not adding any acid nor base, just pure H2O. You will have a certain amount of dissociation of this water into OH and H+. This will give you 10 to the power of 14 and a pH of this water of 7 and a pOH, of course, of 7 too. So that is what we call the pH scale. In this direction you will have increase and decrease, plus, minus, all the way to 14 and all the way to 0. So if you're decreasing now the pH towards 6, 5, 4, 3, 2, of course, missing one 0 here. If you're taking 5, for example, so the pH will be 5, That means that the concentration of H plus in solution will be equal to 10 to the power of minus 5, which is higher than 10 to the power of minus 7, which is at neutral pH. So it's going to be acid. You will increase the concentration of H plus in solution and decrease the concentration of H minus in solution. If you increasing the pH, this value will increase, would be for example 9, the concentration will be 10 to the power of minus 9, which is smaller than 10 to the power of minus 7. Meaning it's going to be basic because you have less H plus in solution. So this is your pH scale, very badly drawn, but the concept is pretty clear, right? This is based on the amount of H plus in solution. So the entire ecosystem, when you have water, you can define a specific pH for a specific body of water in any ecosystem using this scale.